Good evening, everybody. My name's Kevin McConway. I'm one of the Vice Presidents of the Royal Statistical Society, and I'm privileged to be chairing this meeting tonight. So welcome to Fellows of the Royal Statistical Society and to guests. You're all very heartily welcome to the presidential address from our President, Professor Peter Diggle. Peter Diggle is one of the few academic statisticians who really needs no introduction, to a statistical audience at least, but I won't let that deter me. A few words about his career. Peter graduated from the University of Liverpool in 1972 with a BSc in Computational and Statistical Science. Very broad. After a period as a research student at Oxford, he began his lecturing career as a lecturer in statistics at the University of Newcastle upon Tyne. He then went to work in Australia, in Canberra, at the CSIRO Division of Mathematics and Statistics, where he continued work he'd already begun in spatial statistical methodology, as well as carrying out applied work in ecology and in forestry in particular. Peter's ability to combine groundbreaking methodology research with collaborative work with scientists from other disciplines has been a strong characteristic throughout his career. He later went on to develop methods for longitudinal data, which he linked methodologically to his spatial work, but which is again grounded in application. Peter's lived and worked in Lancaster since 1988. His applied interests have moved on, particularly towards biomedicine and health. He's now Distinguished University Professor of Statistics in the Faculty of Health and Medicine at Lancaster University, and also Professor in the Department of Epidemiology and Population Health at the University of Liverpool. And in addition to that, he holds adjunct positions in 3 leading universities in America and collaborates widely in other countries too. Peter Diggle's been involved with the RSS throughout his professional life. He's chaired one of our local groups, chaired the research section, edited Series B of the journal. He served on council, he served on executive committee, and he served on as an honorary secretary. The Society awarded him the Guy Medal in Silver in 1997. Since the middle of last year, Peter has become our president. And I now invite him to give his presidential address on statistics, a data science for the 21st century. Peter.
Thank you, Kevin. Thank you very much for that far too kind introduction. The most important thing in this title is the indefinite article. I hope that by the end of the talk you'll agree with me that that is the appropriate article to put in the title. So, when I started my career, there was an existential threat as perceived by many of my colleagues that statistical packages would make us all redundant. Because why would you need a statistician if a computer could do the sums for you? And that didn't happen. And there are many reasons why it didn't. But the two that I particularly think are important are, firstly, that if something's impossible, it's quite easy to convince yourself you don't need it. And before packages, a lot of scientists just couldn't see how they could use statistics because they didn't know how to, and so they didn't. So the relevance of statistics became obvious when you could actually feed data into a package and get results out. Unfortunately, it wasn't always obvious what those results meant. And so the second thing, the reason why I think packages proved to be a godsend for the statistics profession and not an existential threat, were that it allowed us to be much more useful in working collaboratively with scientists. So although we have the phenomenon of the ubiquitous amateur statistician, because you can go to almost any department of natural or social science in almost any respectable university, and they will claim to have a statistician in the department. Now, sometimes they do, and sometimes they have several, but sometimes what they do have is somebody who isn't a statistician but can do statistics. And we're still here many years later, and I think the current notion that data science is the thing for the future and statistics is a bit old-fashioned, I don't think is really a threat at all. I think it's an opportunity. I am minded to I'm not sure whether I'm quoting Rutherford here or promoting a myth, because there are various versions of this quotation in the literature, but I actually think that version is the one I like because there's an obvious riposte to it. And there's a point to that quote, which is that a lot of people who do data science or label themselves as data scientists and come from disciplines like computer science, machine learning, and so on, they don't talk much about design. And even in our own degrees, we don't talk nearly as much about design in statistics degrees as we did 40, 50 years ago, and I think that's a very bad thing, because I think design is fundamental. And I think the power and the attraction of being able to fit complex models to any data set has actually beguiled a lot of statisticians into thinking that modeling trumps design. And I think sometimes it has to, because there is no design and you're trying to make sense of messy observational data. But I do think it's something that's become underemphasized in recent years and needs to be reinforced. And I'll say a bit more about that later. So I now do what we tell our students not to do, which is go to Wikipedia to find out what something means. So without taking these as authoritative, I think it's quite interesting just to see the kind of words that appear in a place like Wikipedia. If you look at 3 definitions of things which clearly overlap in their scope, and to some people might be preciously close to synonyms, I think there are some interesting differences, interesting nuances, some of which I feel comfortable with and some of which I don't. And it's interesting that right at the top, the thing that I've highlighted in blue is the sort of headline definition of data science in Wikipedia. And I actually think that's a better definition of statistics than is Wikipedia's definition of statistics. Because the one at the bottom is a little bit reminiscent of the collector of figures and the anarchy end of our discipline. And interestingly, information science, which I thought would have a really gee-whiz definition, really does sound very much like the compilation of facts rather than something more imaginative. So I think we've got there is a set of titles which have vague boundaries at best and actually intersect. And I think they can intersect in mutually advantageous ways. And I think the point about my title is that we are one of several academic disciplines that can and should be heavily involved in the 21st century activity, whether it's a scientific discipline or whether it's something else. It might be just an umbrella term. But the thing that is called data science, we are very much part of, but we're not all that's needed. There are other aspects which we need to include. Okay, so if we're going to be part of data science and not say we are data science, go away, we're already doing that, the first thing is to ask what we can offer that's distinctive from other contributory disciplines. And I think preeminently it's the fact that this is perilously close to a quote from one of Dennis Lindley's books, is that probability theory is the definite article, correct way to deal with uncertainty. And in statistics, we do that in 2 really very different ways for which we use the same formal mathematical calculus. Because we use probability when we build models, and really that's a deductive activity, that's mathematics. But we also use probability when we do inference. And that's intellectually, that's a very different kind of activity. But we're rooted in probability, and we insist that that is how you quantify uncertainty. And I think that's something that we can offer more algorithm-based subdisciplines. The other thing that I've already mentioned is that design matters. That data aren't just numbers. This is not an original comment. I'm sure you can find a whole string of presidents of the RSS who've said things like that in various occasions. But that the design matters. When you analyze a set of data, you have to respect the design that led to the collection of those data. And it's not always, in my experience, it is not always true that it is respected as much as it used to be. And critically, that context matters. That it seems to me, going back to Wikipedia's headline definition of data science, you can only extract knowledge from data if you actually have some cognizance of the scientific context in which those data arose. Because knowledge is not just quantitative. Knowledge has a context as well as some purely numerical aspects. So what can we learn from the other disciplines? And I think we've got to the point where it's not enough to publish an article that solves a problem. It's increasingly the case that however elegant your methodology is, if you don't provide code to implement that methodology, other people will not use it. They'll continue to use things for which they have implementations. And the flexibility and power of statistical software has increased enormously in the last 10, 20, 30 years. And it's also become much more accessible with the growth of open source thinking, and in particular the R project that I'm sure most people in this room are very familiar with. And the other thing that I think we should all sign up to is that we've got to the point where a minimum standard of reproducibility of our work should be that computationally driven research findings can be rerun and you get the same answers. When I was editor of a statistics journal with my friend and colleague Scott Ziega from Johns Hopkins, we we ran a discussion piece on reproducibility of research as a kind of minimum quality standard of statistical work. And I was surprised at the extent to which different discussants in greater or lesser degrees challenged this and said it wasn't necessarily a good thing. And I think they were concerned that there might be hints of kind of policing involved there. And that wasn't the intention at all. The intention was that if, however long it is since you've published a piece of work, if somebody comes back to you and wants to sort of pick that up, they ought to at least be able to get to the point where you were. And I freely admit that if somebody comes back with some of my applied articles from 20 years ago and says, I don't quite understand how you could possibly reach these conclusions, my only honest answer is neither do I anymore, because I can't reproduce them. And I think that's the era of that being an acceptable position is closing fast. Okay. Now, you can't talk about data science without talking about computation, and as a little diversion, when I was thinking about putting this talk together, I just had read around a little bit about the history of computing in general, and in particular statistical computing. And I read from the literature that the generally accepted first computer in the modern sense of the word is the Colossus computer that was used for code breaking in the Second World War at Bletchley Park. And around the same time, in statistics, Fisher and his successor Yates were using hand or mechanical calculators, and in particular Fisher's millionaire calculator features on some of the best known pictures of Fisher at work. And while Fisher was running his millionaire calculator in Rothamsted, CSIRO in Australia weren't as advanced as you might think, because in CSIRO in Australia in the 1940s, a computer was a person, almost invariably a woman. And the headquarters of the Department of Mathematical Statistics in CSIRO in Adelaide had a large room which had two doors, one at each end. And there was no obvious reason when I visited for the first time in 1980 why this room had two doors, one at each end. And I was told it was because in the 1940s, the scientist would present the data sheet in at one door, it would pass from desk to desk, and out at the other end would emerge an analysis of variance table. So that was obviously, in a very literal sense, a computer, but it's just that all the electronics were actually replaced by human brains that were programmed to do very specific tasks. Now, when I started my career, as I said at the beginning, statistical packages were just becoming available, and they weren't universally welcomed. And Dennis Evans was a colleague of mine at Newcastle upon Tyne, and he read a paper to the Society, published in 1973, and I remember him being absolutely incandescent with rage when one of the discussants suggested that the way to understand multiple regression was to invert a 5x5 matrix by hand rather than using a package. And I'm sure somebody will say that actually that's a legitimate point from some perspectives, but it does indicate an attitude which I think you certainly wouldn't expect to find today. Now, during the 80s, we kind of began to make the move from packages, which almost, by definition, certainly at the time, implemented a restricted set of methods. So they weren't menu-driven in the literal sense of a pull-down menu, but there was a limited set of options for what you could do with them. And depending on what you wanted to do, you might have to use several different packages at different points in your life. And we moved towards languages and more, which were really potentially much more flexible and at least in principle could be adapted to any statistical task. I'm very fond of the language APL, which I think is now completely defunct. APL stands for A Programming Language, which is not the most imaginative of acronyms. And John Nelder, the late John Nelder, famously described it as a write-only language, because the way APL worked was that it was in the days of, you remember the old IBM golf ball typewriters? And in the standard golf ball, you had upper and lowercase letters. And if you wanted to write an APL program, you had to take your own golf ball and slot it into the machine, and the uppercase letters were Greek letters. And what they were very powerful operators that could do all sorts of things with matrices and vectors, not dissimilar to what S subsequently did, but instead of having nice mnemonic names, they're just these rather cryptic Greek letters. So programs were very compact, and APL had its strong advocates really until quite recently. Dennis Evans was an early one, the late Julian Bezag was another, Graham Wetherill, who was in Kent for many years and then in Lancaster, was a great APL fan, but essentially it disappeared. I've put bugs in there because I'm not an expert, but I gather that bugs was a language before it was a package, if you see what I mean. And again, within a really very wide range of problems, bugs is essentially a language from which you construct a program that fits a statistical model using Bayesian inference. But the big change, for me at least, and I suspect I'm not alone, was when S, as it then was, appeared on the scene. S was described by its authors not as a package, not as a language, but as an environment, and critically an interactive environment for data analysis and graphics. And that was very much the original philosophy of it, I think. What happened then was that people started building things on top of S, and indeed some academics in the University of Washington in Seattle developed a commercial offshoot called S+. And S+ was the precursor of the R culture that's now near universal, where you've got your language, on top of which you've got, at the last count I looked at, nearly 7,000 packages, any of which you can pull in and add on to the basic language. The difference between S+ and R being that the S+ people charged like a wounded bull for you to use their stuff, and you had to renew the license every year, whereas R, as we know, is open source. And if you think about the amount of intellectual effort that people collectively have given freely to the R project, it is prodigious. And the power is really quite remarkable. Now, I'm not game to predict very far into the future, but it may be that there's something radically different going to come in the future. But at the moment, I think R has basically become the lingua franca for statistical research. And not only is it infinitely extendable with packages, but it's also very often linked to other software. So that, as a very simple example, you can call bugs from R, and you can do other analogous things. So I think that's where we are at the moment computationally. Now, I want to move on to the area that Kevin said that I work in mostly these days in, broadly speaking, biomedical and health research. And there's been a real revolution in modern biology over the last, I guess, 20 years. And the statistical potential of modern omics technologies is obvious because they generate prodigious amounts of data, often with a fairly low signal-to-noise ratio, and you need statistical methods to tease out the information in them. The journal Biostatistics was launched in, roughly speaking, 2000, and it had the same editorship for its first 10 years, and it set itself up to be a journal in which it wanted to publish papers that were statistically innovative but rooted in real biomedical or health sciences problems. And so very unscientifically, just by getting the journals off the shelf and looking through the titles and abstracts, I counted roughly the number of genetics omics papers in each year of the journal's first 10 years of its life. And the trend is pretty clear that the penetration of modern biological techniques into biostatistics has been really extraordinary. And in fact, I think a lot of people would almost regard omics and related technology-based statistics as a synonym for modern biostatistics. But the focus, although it's not exclusively this, the focus there is very much on the informatics side of small-scale, molecular-scale research. And if you think about the parallel problem of an informatics-rich population health research, then you might call that health informatics, and that's a phrase that I'm seeing increasingly. It's also sometimes called e-health. E for electronic, of course, and that phrase saw the light of day in particular when the MRC, Medical Research Council, put out a call for the formation of a network of e-health research centres. And in their call for those proposals, what they were clearly aiming at was not the molecular level, the lab-based, the really sort of fundamental science end, but the fact that the NHS in particular has an extraordinary fund of electronically recorded data, most of which is never analysed. And there must be information there that can be unlocked with imaginative analyses in order to actually understand risks to public health, study in a population level causes of disease, risk factors, mitigating strategies, etc. And that was the basis for them setting up this network of e-health research centres. They're now collectively called the Farr Institute, Farr as in William Farr, the Registrar General circa 1840, I think. And there are 4 of them in London, Cardiff, the northwest of England, a consortium of Manchester, Liverpool and Lancaster, and Sheffield, which is not quite York, which is not quite the northwest, and Scotland, which is based in Edinburgh, but is essentially a national consortium. And so that's a network that really is looking at developing something parallel to that explosive growth in molecular level bioinformatics to turn it into population level bioinformatics, or to put it another way, health informatics. Again, Wikipedia, if you believe it's worth the paper it's printed on, defines e-health as healthcare practice supported by electronic processes interchangeable with health informatics. So that's what it is. Now, that's roughly where most of my current work is focused. And so what I want to do now is really just give you a brief account of some case studies in which I've been involved recently, which I think and hope illustrate the potential for innovative statistics to add value to health informatics, but also to emphasize the fact that if you really want a complete solution to a problem that will actually change public health practice, then statistics is not enough. You need informatics as well. And in the sense that I'm going to illustrate that in these next exercises, you can think of informatics as pretty close to being software engineering. So that the idea is that you can solve the problem in a methodological sense, but if you're trying to influence public health practice, you need to deliver that solution to public health professionals who will not be statisticians, they will not necessarily be scientists, they will be decision makers, and they need solutions that appear as products on their computers in their offices that can help them in their decision making. So a paper in the journal Biostatistics is of no use to them whatsoever. It's not to say we shouldn't still write those papers, because we've got to make a living, and we will continue to do so. This is really just a slide I need to use when I'm giving versions of this talk to a non-statistical audience, because it's again picking up this theme that just as I would say statistics isn't all you need to be a good data scientist, equally I object to anybody who claims that informatics is just about computer science. Statistical method is needed because data is always a combination of signal and noise, and if you're doing population health research, the noise often dominates because you can't do controlled experiments on population level on people. You have to deal with all sorts of extraneous variation. And so I think of stochasticity, probability again, as the kind of honesty box that we use here. And of course that's not context specific. And two quotes which I very strongly subscribe to, one by the late John Tukey, one by the not so late Peter McCulloch, I think nail down the idea that a lot of what we do is about prediction, predicting what's happening. It's not necessarily, somebody once said forecasting is very difficult, especially when it's about the future. But actually forecasting the present is pretty hard sometimes. So understanding the signal underlying what you're seeing in current data is a probabilistic problem, and you need to give a probabilistic answer. And you can think of a probabilistic answer as an approximate answer, although that's not quite the sense in which Tukey meant that word. So refusing to give a simple answer to what other people think is a simple question is our way of saying it's not actually so simple. And I could pretend it was and make you happy, but I wouldn't be being honest. So here's the first one. This actually is quite old. These slides, which are actually produced by my friend and colleague Barry Rollinson, who's lurking somewhere in the room, were produced back in about 2002 or 3. And the background to this case study is that round about 2000, some people in the Public Health Laboratory Service in Southampton, which you will recognise is on that map, that's the county of Hampshire, came to my research group in Lancaster with a proposition that they were concerned that in trying to sort of spot unusual patterns in people reporting symptoms of gastroenteric illness, vomiting and or diarrhea, which might be early warning of a public health outbreak, the kind of systems that were in place in 2000 had two very major faults. One was they're very incomplete, because only a small fraction of the people who are ill with vomiting and or diarrhea ever turn up to a health professional. And secondly, it took up to a fortnight to actually get a diagnosis from somebody who turned up and did present symptomatically to their general practitioner or to their local hospital and was dealing with. So you basically missed most of the cases, and the ones that you did see, you saw very late, and the horse may by then have bolted. So the proposition that they put to us was that couldn't you use spatial statistical methods to produce more timely maps of where there seems to be some unusual incidence pattern of gastroenteric illness in the county of Hampshire. And the project almost died at birth because the original proposition was to use general practices to report data daily. And general practitioners were by and large too busy to do that. So typically we got 0, 0, 0, 0, 0, and then a lot of cases. And it was a very happy coincidence that NHS Direct came online about that time, and for me, a very sad event when that was replaced by a whole bunch of uncoordinated NHS 111 services. But at the time, we had a very simple protocol operating county-wide there, in which, at midnight every day, we could get the residential postcodes of all of the people who'd phoned into NHS Direct complaining of vomiting and or diarrhea. Now, that's not a diagnosis, but if you have a historical record of the patterns of those calls, and you can therefore look at adjusting for things like seasonal variation in county-wide incidence and geographical variation because of the demography of people who use NHS Direct. I don't think my mother will ever use NHS Direct, she's 91, but people with young children often do. So we're talking about a particular population here that's not the complete population, but as long as it's consistent, what we can do is use the historical data to correct for the overall time trends and overall geographical variation in the incidence of symptomatic reporting of this kind. And then we can probabilistically say where in the county on the 8th of March 2002 is there strong evidence, meaning a high predictive probability, of the current incidence being at least twice what we would expect for that place and that time of year. And in the implementation that Barry wrote, you could click on different dates, you could click on different exceedance thresholds. This is for a doubling, you could have a quadrupling, you could have an octupling. And you can see that the colour scale on the map is deliberately chosen to make almost everything green. And equally, I can't imagine the Public Health Laboratory Service would get out of bed for a doubling of incidence. So the map is presented there, so there's actually something for you to see. If you run these maps at an operationally relevant level, they're mostly green all the time, which is as it should be, because if we're having outbreaks all the time, we'd be kind of worried. Now, the statistics there, the only thing about it that's really not routine is that we model the unexpected components of incidence as a log Gaussian stochastic process, a log Gaussian Cox process, and it's that enables us to translate the incidence into a probabilistic statement about the current rate. And so what we're mapping there is predictive probabilities of exceeding a threshold that somebody else, in principle, should tell us is of public health significance. Okay, and that project died because it ran out of funding, and it has recently been revived with another tranche of funding, and we're now working on actually implementing this on a much wider geographical area, and also running a parallel veterinary surveillance system. And if we do find any commonality between anomalous patterns in both the human and the veterinary patterns, that will be extremely interesting and will tell us something about cross-contamination phenomena. But clearly, and I don't want to embarrass him too much by mentioning his name too often, but there's no way on earth I could have produced that output. Barry did all that with his knowledge of programming and building web-based tools, but the public health people in Southampton got that map every morning, updated automatically. The analysis was triggered at midnight, an MCMC run went on for several hours, and the predictive map was posted. And they were able to say, that's unusual, maybe I should look a bit harder there. And then the next day, if it goes away, I'll stop worrying, but if it's still there, maybe I should do something else. So the idea is not to produce a definitive answer, but to produce an approximate answer to the question, is there anything unusual going on? And the decision to act on that evidence would be, in my opinion, best left to the professional. So this is not about making the professional's decision for them, it's about informing them what the evidence is in the data about the decision that they need to make every day as public health professionals. Is there something I should be worried about in the southwest corner of Hampshire, for example? A long time ago, a friend of mine who's a medical statistician, he said he was at a dinner party and somebody said, as a statistician, what would you advise me about having my child vaccinated against measles, mumps and rubella? And his answer was, as a statistician, I would advise you to talk to your doctor. And I think that's basically my own position. I've also lost my pointer, I don't know where I've put it. Oh, thank you, Kevin. Look behind you. Yes. Okay, thank you. Right, second page 3. Our dear government, one of the good things it did, I better not say what I was going to say. One of the good things it did was make publicly available a comprehensive record of NHS prescribing patterns by month and by GP practice all around England, as you can see. There's no data there for Wales or Scotland or Northern Ireland. And what you've got there is, for one particular month, the average spend per patient by each GP practice on Ritalin, which is the frontline licensed drug for treating attention deficit hyperactivity disorder. And there's huge variation. You can just about see that from something between 0 and 10 pence in dark blue to something of the order of £2 in dark red per eligible person per GP practice. That's a huge variation. Now, of course, a lot of that is noise. And people come and go presenting with different conditions, and so you can't just rely on a snapshot of the data to draw any conclusions. But what you can do is present various statistical filters. And what this filter is doing is saying, show me where there's a high probability that the local rate is at least 4 times the national rate. Now, I invented 4 because I don't know, what would be a reasonable threshold in this case. But the point is that then that map rather forces you to look at a much reduced number of areas, one in the southeast, one in the northwest, and one in East Anglia. And I'm going to focus on the northwest because that's the area I know best. And if you then simply zoom in on the map, and now this is actually not, there's no statistical smoothing being done here anymore. This is just the data. But the point is we've now identified this as an area to zoom in on. And if you know your Merseyside demography, the Wirral Peninsula, which is south of the Mersey, is largely leafy and middle class. It's a slight oversimplification, isn't it, Helen? But, it's roughly like that. And north of the river, there's an awful lot of poverty and urban poverty. Now, I don't know what the explanation is for that discrepancy, but it's clearly not just 1 or 2 rogue GPs. It's clearly a very strong pattern. And I'll leave you to decide whether it's to do with over-prescribing in the leafy suburbs or under-prescribing in the poor quarters of Liverpool. But what it does is it flies in the face of any notion that we have any equity in the delivery of healthcare. They can't both be right in the way they're dealing with that problem. Okay. Now, the third one I want to talk about is again pretty close to home in the city of Salford, the Salford Integrated Record System. Again, this is a very visionary project initiated not by statisticians but by clinicians and health professionals to assemble in a single server all of the primary and secondary care data for people who live in the city of Salford, and in principle to make those data available for bona fide researchers to address questions of scientific or public health interest. Updated every 24 hours, an immense source of information. The particular problem that my group was approached to work on a few years ago now by the renal physicians in Salford was the following. When people's kidneys are failing, typically, not universally, but typically, it's a very slow and inexorable process. And in particular, it's asymptomatic for many years. And although most cases of kidney disease are irreversible, the speed at which your kidneys are failing can be ameliorated by interventional treatment, principally the aggressive control of blood pressure. But because it's asymptomatic, very often people go undetected for many years before they're referred to specialist care. And the proposition put to us by the kidney physicians in Royal Salford Hospital were that if they knew that somebody was losing 5% of kidney function per year, they would say they should be considered for referral to secondary care. So to translate that into a statistical problem, you have one of the 22,910 data sets we've got on the left-hand panel there, which is measured kidney function, and it's very noisy. The assay that's used to estimate kidney function has a very high coefficient of variation. Well, it's not just a coefficient of variation. It does have a literal measurement error in it. If you split the sample, you get 2 different answers. But it's also susceptible to extraneous things like your general fitness, your body, your muscle mass, and various other things. So it does tend to bounce around a lot. And if you look at that left-hand panel, then it's clear that, with the benefit of hindsight, at some point this person has got a real problem with their kidneys and they ought to be referred. But if you can imagine that a primary care doctor looking at these data in real time as they accrue, at what point would they say, I think I need to refer this patient? So we took that as a statistical problem in which we said, let us now estimate the rate of change of that kidney function measurement, and we'll do it by postulating a model in which we combine things we understand, which are covariates, Xij prime alpha, that we know affect the state of your kidneys, of which the first one is age. All of your kidneys are failing, but don't worry about it, because in most cases they're failing very slowly. Person-specific things, UI, are just things which say some people have inherently better kidneys than others, but critically, there's a time-varying stochastic process, and it's the slope of that stochastic process that we're actually trying to predict. So in the middle panel, you have the point predictor of that stochastic process, the conditional expectation of the slope, given the data to the left, not given all the data. But on the right-hand panel, you have the predictive probability that the expert clinician's intervention criterion of a 5% loss has been met. Okay? And again, I don't think it's my business to say at what point the physician should say, go to secondary care, but the point is that it's the picture on the right and not the center or the left picture that allows the physician to make an informed judgment of what their patient's system is doing relative to the expert's declared criterion, right? So if you could directly physically measure loss of kidney rate, you would actually want to know for sure, is it greater or less than 5%? In the real world, you have to take a punt. And if you wanted to take a 50-50 punt, you'd have referred them after about a year. And if you wanted to be nearly certain, you'd have waited another 6 months. And I can't decide what the right tactic is, but what I can do as a statistician, what you could all do as statisticians, is turn the clinician's criterion into an honest statement of the probability that that criterion has been met. Now, I don't have the ages of this patient marked, I just have their follow-up times, but there are many reasons why somebody who is meeting that criterion might still not be eligible for specialist kidney care. They may have other conditions which preclude any aggressive intervention, for example. But it translates the problem into what I think is the right question, rather than just estimating parameters. It's a predictive problem. What is the probability that a certain criterion put by an expert has or has not been met by each patient in that database? And again, to turn that into a useful tool, we can't stop there. What we have to do, and we've just started working with the people at the Fire Institute in Manchester who are much stronger than us generally on the computing side, to turn that into a tool that can actually be sitting on the doctor's desk when you turn up with your latest blood result and ask for advice as to what your treatment should be. Okay, I think this is my last example. It's always nice to remember that data are often hard won. And the man on the motorbike is an epidemiologist, and he's away from home probably for about a month. And when he left home, he was driving a Land Rover. But at one point, the road ran out, so he unhooked the motorbike from the back of the Land Rover and carried on, because what he has with him is a list of villages he has to find. And when he gets to those villages, he has to get some data. He has to take some blood samples. And based on those blood samples, we can tell whether that person is or is not infected with a parasitic disease. Okay? The goal of doing that is to produce a map which shows you where this disease, onchocerciasis, or commonly known as river blindness, has high prevalence, where it has low prevalence, because Merck, big pharma company, has donated, for as long as it takes, free drugs that can be used as a prophylactic against river blindness. But because as long as it takes could be 25 years, the people who are running that program in Africa need to prioritize the high-risk areas. So if you've got a map of prevalence, you can say, we've got a big problem here, we'll do this first. And where there's not much of a problem, they might have to wait, because the resources within Africa to do this kind of work are clearly very limited. Even though the drugs are free, the operational business of dispensing them is a real stretch on available resources. Now, that program was running quite happily for a number of years until it was noticed that this prophylactic medication, which is given to everybody in a high-risk community, sometimes had unpleasant side effects and very occasionally killed people, which is rather unfortunate. Out of 40 million treatments, it might have killed 200 or 300. And there's an interesting sort of ethical question there as to, risk and benefit. I'm told anecdotally that most of the village elders, when told this, said, well, we'll still have the pills, thank you very much. But certainly in a UK setting, this would be, headlines in the Daily Mail, presumably, doctors killing patients, etc. But for whatever reason, it was a problem. And there was a rather ingenious scientific solution to the problem, which is that if somebody is co-infected with river blindness parasites and a second parasite which causes a rather less severe disease called lower or eyeworm, whoopsie daisy, then it's that heavy co-infection that puts them at risk of the serious adverse reaction. Because basically when the pills break down the parasites, the byproducts of that reaction set up an antagonistic reaction, right, if they're there in high enough density. So the program was temporarily, it wasn't halted, but it was slowed down by the fact that even if you could see that this area was a priority for treatment for river blindness, you also had to go and map lower and find out if it was also at risk of the serious adverse reactions. That was still very much a sort of a rather crude exercise, because if you think of Tukey again, better an approximate answer to the right question than a precise answer to the wrong question. You really don't want, when you go to a community, necessarily to just say, have we got high prevalence of both diseases? What you really want to know is there a chance that there are people in this community who are at risk of the adverse reaction? And because of as the biology was better understood, and it was clear that the people who were at high risk were those who were very heavily co-infected, then even in an area which has high prevalence at a population level, it may be, or it may not be, that there's an acceptably small proportion of people who are at individual risk of the adverse reaction. So that's the real question we want to answer, is what's the probability that somebody is sufficiently highly infected to be at high risk of an adverse reaction? So going to the bottom of that slide, the target is the probability that somebody's level of infection is over a threshold C, which, not wishing to put you off your dinner, is either 8,000 or 30,000 parasites per milliliter of blood. Okay? How do we get to that point? Well, we need to build a model. And fortunately, we've got data from a selection of about 200 villages in the overall program areas, where we can look at the actual level of infestation. And in particular, on the top right there, you've got a genuinely random sample of 5 of those villages. It might even be just 4. Anyway, not many. And you can see, because the diagram doesn't go all the way down to 0, that prevalence here is somewhere between 30% and 10%. And then after that, you get this characteristic convex curve of increasing levels of infestation. So after a fair bit of data analysis work on these 200 villages, we came up with a model in which, in any village, we could get a reasonably good fit to a viable distribution for the level of intensity conditional on it being positive and a chunk of probability at 0. What we find is that the parameters of that distribution vary substantially between villages, and so far we've not been able to find an effective covariate to predict that variation. So we model it as a random effect. Stochasticity is our honesty box again. It's a metaphor for ignorance, if you like. We don't know why the prevalence varies between villages, so we'll model it as a random effect. And when you actually then fit that model, what you find rather nicely is that if you look at the point predictors of the random effects for prevalence and for rate of infestation given a positive result, they're very highly correlated. And so that correlation gives you the power to predict the proportion of people who are highly infected given only the prevalence. Now, why is that useful? It's useful because if you think about where this chap on the motorbike was working, oh dear, that's bad, I'm going the wrong way. A, there's not a lot of money around in places like this, and B, it's not the sort of place where you want to go casually pricking people's fingers and letting insects help themselves to the blood that comes out as a result. So you can estimate prevalence, it turns out, by a non-invasive, simple, cheap technique, whereas to actually measure infestation rates, you need to do some more refined laboratory work, which is expensive and potentially a bit hazardous. So the proposition is that you can get a predictive estimate of the proportion of highly infected individuals in a community simply by observing the prevalence in a sample from that community. Now, this becomes informatic because the question then is, how can you do that in the field? And the point is that once you've fitted this model, you can actually convert it. I can't, but I am assured it's technically, by modern standards, relatively straightforward to turn that into a mobile phone application where people can basically feed in the prevalence and come back with the predictive probability and then make an operational decision in the field as to whether they should go ahead or whether they should set up precautionary measures to treat people who have the serious adverse reaction. Basically, if you catch people straight away, you can save their life. If you don't do that, if you just leave them with the pills, then they're a long way from the nearest hospital and they're at risk of death. So that's that. Okay, so I'm just about done now. I just want to finish with some very general remarks about our discipline. And the first one I want to emphasise is something that really, I believe this dichotomy was introduced by John Nelder in a letter to RSS News and Notes when that was still a paper document. And he said that mathematical statistics should really be called statistical mathematics. And I rather like that because it allows us to do two things, both of which I think we should always be pushing. One is that statistics is intimately bound up with mathematics and with the mathematical sciences, and we therefore can, should, and must work across the mathematical sciences together to make sure that the government gets it and continues to fund the mathematical sciences to the level they should. But at the same time, when we're talking outside our own comfort zone of the mathematical sciences, if you like, the word statistical science emphasises the context-dependent nature of a lot of what we do. And I personally find that a more informative phraseology than saying theoretical and applied statistics. Very theoretical work in a mathematical sense can still be very applied if it's being used to solve a scientific problem. So I think we need to know when we're operating as scientists, typically collaboratively, and we need to know when we're operating as mathematicians, and we need to continue to do both if our discipline is going to continue to thrive. That then raises the question of where should statisticians sit in a research organisation. And what I would really like them to do, if I was, the czar for everything on the earth, as it were, would be to encourage universities to think about making most or possibly all of their statisticians joint appointees. And the way I would structure that is that every statistician would be a member of a statistics institute, but they would also be a member of a department. And for many of those people, that department would be mathematics. For some of them, it might be computer science. For some, it would be biology, economics, sociology, whatever. The details would differ from institution to institution. But critically, those people need dedicated time and space to meet and share ideas. And I'm very much driven by that by my experiences in Australia in the early 1980s, where the CSIRO statisticians had 2 offices each. They had their statistics office where they met and shared ideas, and they had their science office where they shared other ideas. And so the science benefited from the collective input of a large group of statisticians, and the statistics benefited from the stimulation of a large variety of scientific problems. Now, we can do this by stealth, because we simply have to insert ourselves into every data science institute in the land and be a benevolent parasite in everything that they do. So if that's an acceptable position, what should we be teaching our students? And I think that the discipline's now reached a level of maturity where we should stop teaching courses on specific methods. I personally have never taken a course in longitudinal data analysis, or survival analysis, or categorical data analysis, or a lot of other things. But I hope I'm competent in most of them. But I could never have got started as a research statistician if I hadn't had a thorough grounding in the fundamentals. Firstly, a fair chunk, even if it's misspelled, of mathematical foundation from my first degree. Secondly, courses on design and courses on probability and stochastic processes. And I often thank my lucky stars for the fact that quite by accident I came to statistics via stochastic processes. Right? I actually thought I was going to do a PhD in stochastic processes, and gradually I realised that actually I was more interested in what I would now call statistics. But I'm glad I had that grounding in stochastic processes, because I think it's fundamental to what we do. And with modern computational tools, if you know how to use them, it seems to me if you really understand probability and you really understand likelihood, that's just about all you need, really. Of course, there are a lot of subtle skills and not so subtle skills in applying statistics in particular contexts, like longitudinal data, time series, survival analysis. But I actually think, going back to the top of that slide, they're much better taught through projects than through lecture courses. So the computation line is there because by that I do not just mean using packages. I mean that the standard of programming skills that statisticians typically have is very low, and I know from some of my colleagues that where you have a much higher level of skills, there are things that you can do that you just can't do if you're writing really bad, inefficient, clumsy code. So I'd like to see some serious boost to the way computation and computational science is treated within our statistics degrees. I'd like our students all to be able to write. My favourite story there is that when I taught a course in scientific writing in Lancaster to an MSc class, about half of whom were from the UK and half were from various European countries, I said one of the pieces of advice I'd give you is to write in the active sense. And all the European students nodded and the British students looked puzzled. And I think we need to actually change that. And also, I find it ironic that we would expect a biology degree to include some statistics, quite rightly, but we don't expect a biostatistics degree to include any biology. And I think we should. I think if you want to give people a rounded view of our subject, you want the maths, but you also want the science. Now, which science could be a free choice for the individual, but I think unless you actually understand both of those things, you're an incomplete statistician. Okay, I'm really pleased that the Society has taken a lead in moving towards the introduction of what's called core mathematics at high school, where the ambition is that everybody will do mathematics, which includes a substantial chunk of statistics, irrespective of what their main discipline is going to be. I think when people get to university, I still would like to see less statistics in undergraduate degrees and more maths, provided that maths includes stochastic maths in large measure, and I'd like to see more computing. When we get to MSc, that's where I think you can really make yourself into a statistical scientist. Again, with this view of not having endless lectures on particular methods, but having projects and genuine dialogue with scientists to build that dual skill of being mathematically sophisticated and scientifically aware and sensitive. And I would like to see the research councils funding linked PhDs. Why not have 2 PhDs funded by the MRC with the same title, one of whom does the quants and the other of whom does the lab work, and they put a joint thesis in. I think that would be a much better training than our current approach. Postdocs, I think there the opportunity is to get migrants in. And the MRC is doing that with its training fellowships. The research councils generally are very receptive to putting more money into training in quantitative methods, including migrants from other disciplines, and I think we should capitalise on that. I think we have to question what our journals are about, and we're going to have to question it commercially, even if we don't want to question it intellectually. Once I got into medical research, I immediately realised that you expect to get a turnaround from a paper you submit to a medical journal in weeks, not months. And I do not understand why we can't move to that in statistics. And I think the fact that we don't move it in that direction means that a lot of really good, modern, innovative statistics is not being published in statistics journals. Sorry, I should say biostatistics, because that's all I know about. It's being published in genetics journals and biology journals, because they're current. And in that world, archiving your results after 6 months is not helpful. You need to be out there as soon as the results are there. I think we should publish very short papers and aim for our papers to be more intelligible to a general scientific audience than they typically are now, and make much more use of supplementary material like the really big science journals do, like Nature and Science, so that people can follow up the details and reproduce the results because you've got code and data there, but their headlines are conveyed in a way which is intelligible to a general audience. And I do think part of that ought to be minimum standards of reproducibility, allowing people to comment in the way that, for example, the BMJ, as soon as you publish a paper in the BMJ, it's open for comment, and comments are there on the web, and people can say it's a load of rubbish if they think it is, and that's, I think, all very healthy. And sort of closing, perhaps, with trying to make this something like a presidential address and say, what's the implication for the society as a whole? Well, the society has already got a view, a very constructive view, on the debate between public good and individual confidentiality. And it's clear that to unlock the potential of electronic data sources to the full, you have to decide how much you're going to sacrifice for individual confidentiality. If you go back, for example, to my maps of prescribing for attention deficit hyperactivity disorder, the government has decided that it's okay to have a map in which you can see which GPs are over-prescribing or under-prescribing. It would not allow me to point to the actual people that are getting the medication, and those data are not available. So there's a balance, and there has to be a balance. We should see the irresistible rise of informatics as an opportunity rather than a threat, and we should be more and more engaged with other disciplines, and we shouldn't be too worried about terminology. We shouldn't be too worried about people calling us data scientists. If we can come to the party, I'd rather be involved than worry about having rather dry debates about what is and isn't statistics. And finally, just as a personal note on which to finish, it would be a mistake to think that high-tech solutions are only for the developed world. The deep penetration of the internet and mobile phones into very remote and poor communities in Africa is quite startling when you first see it. And there really is a potential there to transform people's access to information, education, health, and all sorts of other things. Thank you. I'm done.